Good afternoon. Welcome to the second talk or colloquium in this summer semester's series. We have again one of our own professors speaking today about the instrumentation and the science done with these instruments up at the State Observatory on the Königstuhl Mountain. Andreas Quirrenbach will be talking to us about CARMENES, this very high precision spectrograph that is currently built, or is actually operational, right? On the Cala Alto Observatory, and he will in particularly talk about how to hunt for blue planets orbiting red stars.
Good. I'll switch on the microphone and welcome. This afternoon I'm going to talk about CARMENES, which is both an instrument and also a scientific project. The acronym actually tells it all. I could just stay with this view graph and that's the whole story. The acronym stands for, first of all, where the whole thing is at Cala Alto Observatory. What we are doing a search at high resolution. We are looking at M dwarfs, and what we are interested in is Earth-like planets, exo-Earths, and technically what we built is two Echelle spectrographs, one working in the optical wavelength range and one in the near-infrared. And I will explain why we did that given our scientific goals. So that's one of the main purposes of this talk, is showing how you start with a scientific goal and then from that develop a concept for an instrument, build it, put it into service, and then start doing science with it. So just a quick reminder, I presume that everybody here has heard about the radial velocity of looking for planets around stars other than the sun. What we are looking at is the motion of the star around the common center of motion, and in this technique we detect this motion through the Doppler effect. And it's quite useful to keep some of the scaling relations and rough numbers in mind. So for the Earth, the motion of the sun has an amplitude of 9 centimeters per second. So the orbital velocity of the Earth is 30 kilometers per second. The sun is 100,000 times more massive. And then, 300,000 times more massive. If you divide 30 kilometers per second by 300,000, you get to roughly 10 centimeters per second. So we're looking for really small Doppler shifts. And the scaling is such that so first of all, it's proportional to the mass of the planet. More massive planets are easier to detect. Then it's proportional to the mass of the star to the -1/2 power, and the distance from the star to the -1/2 power. So it's easier to find planets around less massive stars, and it's easier to find planets that are in closer orbits. And this is one of the reasons why we are going to M dwarfs. So as I mentioned, this is all being done at the 3.5 meter telescope on Cala Alto, a nice telescope that has been there for a few decades. And this is now a new instrument on this telescope. The consortium that does this project is relatively large. We have 5 institutions here in Germany. We have 5 institutions in Spain, and the observatory itself is also involved. So that reflects the fact that Cala Alto really is a German-Spanish observatory, and we started this project right from the beginning as a common joint German-Spanish project. So let me come back to the question, why are we particularly interested in M dwarfs? The first reason is, well, if you are going to look for a planet that is potentially habitable, you have to look at the distance from the star where water can be liquid. This is the so-called habitable zone, and it's sketched here as this gray band. So here on the x-axis is the orbital distance. Here is the mass of the star. So here we have a solar-type star. These are the Earth, Venus, Mars, and depending on how optimistic or how conservative you are, Venus and Mars may just be inside or just be outside of the potentially habitable zone of the Sun. The Earth certainly is inside the habitable zone. Yeah? Yeah?
Sorry, does that include any greenhouse effect, or is that just from the location around?
Yeah, so this, the question is about greenhouse effect. I think this band does include some assumption about the greenhouse effect. Now, talking about a habitable zone is a gross simplification. The habitable zone, in the way I plotted it, just depends on the parent star, and it's just the distance where water can be liquid. And of course, this depends also on the planet. If the planet has a denser atmosphere, it will have more greenhouse effect. So just plotting this as a function of distance of the star is a simplification. And you take some average for the greenhouse effect, for instance. There are other simplifications here. For instance, this concept neglects that a star may have huge ultraviolet output, which may destroy the atmosphere. So this is a problem for M dwarfs. Yeah, you may think that M dwarfs perhaps do not even have a habitable zone because there may be so much UV radiation that planets can't survive. But we neglect this here for the time being and just say, well, we look for planets that at least are at the right distance, that are moderate temperature, the size of the Earth, and the same amount of flux integrated over the whole spectrum from the star. And then as you go down in mass, of course, the stars get much less luminous, and this habitable zone moves in. So the orbital distance of the habitable zone for a late M-type star is at a distance of less than 0.1 astronomical unit. So here you see the first advantage. If you are interested in habitable zone planets around M dwarfs, first of all, the star is less massive, and second, the habitable zone is at a smaller distance from the star, so you gain twice in this formula. It's easier to find habitable zone planets around M dwarfs than around the Sun, and that is shown here. These lines are kind of constant precision that you need. So here, this is an example for a planet that has 10 Earth masses. If you have a measurement precision of 1 meter per second, and each data point you want it to be 2 sigma, then you are on this line. And so you can see these 10 Earth mass planets with a few measurements in the region that is to the left, and that means for the Sun, the whole habitable zone is outside of the range that you can measure. For a mid-M-type star, the whole habitable zone is inside at a given precision of your measurement. So this is the first advantage of M stars. Amplitude is larger. The second advantage is, if you are looking in this region, of course, the orbital period is also shorter. Yeah, the orbital period of the habitable zone in this range is something of order 2 weeks, 3 weeks, 4 weeks. That's much nicer if you observe from the ground than having 1 year, which is the habitable zone period for the Sun. Because if you have the 1 year period, you always have these nasty problems that you can sample for 1 season, for a few months. You can observe the star, then it's not observable because it's up during the day, and then you get some more data points the next year. You can never really cover a full orbital period nicely. It takes several years. Here, you see with these kinds of periods, we can observe a planet in one observing season, which may last 3 or 4 months, we can observe it every day, and we see 3 or 4 full cycles of the radial velocity in one observing period. That's the second big advantage. So then we picked M stars close to the sun, so in our neighborhood. And here's roughly our sample. So what we did is we divided the M spectral class into subtypes, M0s, M1s, M2s, M3s, M4s, M5s, and so on. One thing to realize is that the range spectral class M covers a very large range in mass. If you look at the masses here, there's at least a factor of 4, and in principle it goes down another factor of 2 to the hydrogen burning limit. So if you think about an interest, if you have an interest in discovering how planetary systems vary with a stellar mass, because the star formation process generates different disks around stars of different masses, so stars of different masses form different types of planetary systems. M stars are a great class of stars to study, because if you think about it in a logarithmic space, M here is a factor of 4 at least in mass, and that is more than F, G, and K together. So by splitting our M range in this way, we can really study, without ever doing anything else, but looking at M stars, we can study how stellar mass influences the outcome of the planetary system formation process. The other thing that is nice about M stars is they are close. The mean distance of our sample is only 13 parsecs. So unlike other methods, which are interesting but give you planets that are at distances of typically hundreds of parsecs, or some even, like microlensing, looks at planets that are kiloparsecs in distance, these are very, very nearby. And very, very nearby is great, because we can also learn a lot about their parent stars, and because they are very suitable also for follow-up with space telescopes, like the James Webb Space Telescope, to do spectroscopy. So we are really looking in the solar neighborhood. And of course, you may have heard in the past few months that other groups that have started also to look at M stars have found some very interesting systems, Proxima Centauri, TRAPPIST-1, and so on. So we are going to do in principle the same thing, but in a more systematic way with a larger sample of stars. We are looking now at something of order 300 stars. So the numbers here are a little bit larger, but this is the total from which we will pick the best stars. We cannot do all of them in the time that we have. So the goal of this M-dwarf survey is to get radial velocity curves of 300 such stars with a precision that is good enough for terrestrial planets. We are interested in orbits, in multiplicity, in the architecture of these systems. They are very nearby, and we should statistically find also a few planets that are transiting, and they are even better for follow-up, because then you can do transit spectroscopy of the atmospheres. We are also collecting very detailed information on their parent stars. So the spectra that we are getting are better than anything that is currently there in terms just of spectra of M stars. We get high-resolution spectra covering the whole wavelength range from the mid-visible at 0.53 microns out to 1.7 microns. We have key activity indicators. I'll show a few examples a little bit later. So these are indicator spectral lines that tell you whether the star is active or not. And we get line variability. We can look at the radial velocity variations. So we can also learn a lot about the stellar physics. And we need to learn a lot of the stellar physics. So when we started this whole thing, we ran some simulations of what we could detect, and with the goal that we have of building an instrument that can measure to a precision of 1 meter per second. This is this line here. These are all stars in our input list, and this is the detectable planet mass in the habitable zone. So for each of these stars, we have put the mass in here that we could detect if there is such a planet in the habitable zone. So this point here, for instance, means around this star, we could detect a planet in the habitable zone if it has at least roughly 2 Earth masses. So I have color-coded these diamonds here with the rotational velocity of the star, v sin I. And you see that by and large, the ones that have low v sin I are at the bottom here, and the ones that have large v sin I are here. Not nearly as good. So you may ask the question, why is that? Why is it easier to find low-mass planets around stars that are slow rotators? Well, we have to talk a little bit about the measurement precision. And here it's very important to realize that the precision of the measurement is not the resolution of the spectrograph. These are two different things. So let's first start with the observed line width. The observed line width, delta V, is essentially the maximum of either v sin I, so that's the rotation of the star, the rotational broadening. If you look at it pole on, then sin I is 0, then you don't see any line broadening due to rotation. If it is equator on, you see V fully. So if the star rotates relatively rapidly, v sin I is large, and the observed line width is essentially v sin I. If the rotation of the star is very slow, or if your spectrograph resolution is too low, then you are limited by c divided by the resolution of the spectrograph. So the resolution of the spectrograph is defined as lambda, the observing wavelength, divided by delta lambda. And delta lambda is your usual kind of Rayleigh criterion. How far do two lines have to be separated so that you can see them as two separate lines rather than one line blended? So typical numbers here, if I build a high resolution spectrograph, a good stellar spectrograph will have a resolution of roughly 100,000, and that corresponds to 3 kilometers per second. C divided by 100,000 is about 3 kilometers per second. And this is also kind of a typical rotation velocity of the star, and rotational broadening is normally the dominant mechanism in these stars. So this is the observed line width, about 3 kilometers per second. The star is a rapid rotator, a bit more. So now the precision that you can get for measuring the centroid of a line is this width of the line divided by the signal-to-noise ratio. So this is an incredibly important formula, and for those of you who still have a PhD defense ahead of you, you better know this. This is important everywhere in physics, so it's important here for measuring the centroid of a line in a spectrum. It's exactly the same, for instance, if you ask the question, how well can Gaia measure a position of a star? If you want to know how well Gaia can measure the position of a star, you take the resolution of Gaia. So now in angular units, something of the order of, 50 milliarc seconds, 100 milliarc seconds, 100 milliarc seconds. You count the number of photons that Gaia will collect on the star in the mission lifetime. You take the square root of that, you divide 100 milliarc seconds through the square root of the number of photons, and you have the measurement precision of Gaia, at least for the fainter stars, where you're not limited by systematics. So you do exactly the same here, if I want to know how well can I measure the position of a spectral line in my spectrum, I take the width of the line, which is typically 3 kilometers per second. I divide by the signal-to-noise of my spectrum, and I typically take spectra with a signal-to-noise ratio of 100, so 10,000 photons per resolution element, and that gets me down to 30 meters per second. That's how well I can measure the position of one line. Now, what I'm really interested in is the radial velocity of the star, and the star has very, very many lines. So if I average over, say, 1,000 lines, each line gives me a statistically independent measurement of the radial velocity of the star. So the precision with which I can measure the radial velocity of the star is this delta V with which I can measure a single line divided by the square root of the number of lines, and that is 1 meter per second. So don't get confused about this. This is very logical. We have a spectrograph resolution of 3 kilometers per second. That is, two lines will be separated if their separation expressed as velocity is 3 kilometers per second. But the precision with which I can measure the spectrum, just from the photon noise point of view, is 1 meter per second. So this is the statistical noise in my spectrum from the photons. The challenge is to build a spectrograph that is stable at this 1 meter per second level. But in principle, this very quick calculation tells me it can be done. And so here are the rotation velocities of a sample of M stars and brown dwarfs. So the stars we are interested in mostly, this pointer keeps fading out, so I have to show here with the analog pointer this. So this is very large. There is a choice here. Yes, this may be. Okay, so we are mostly interested in stars down here in this M range, not so much in the brown dwarfs, which are just too faint. So you see that quite a few stars exist in this range that have rotation velocities of 3 meters per second or even a little less. And there are some that have higher rotation velocities, so this will not be so good. But there are many stars that we can look at that have 3 kilometers per second or so. So this is the first important input in our design of the spectrograph. We can ask the question, what resolution should we give the spectrograph? Should we build a high resolution spectrograph, a low resolution spectrograph, something in between? So here we plot the V sin I of the star, and here we plot the accuracy with which we can measure. You can slide the whole thing up and down depending on your integration time. Yeah? So if you integrate longer, the whole plot, all graphs will move down at the same rate if you integrate longer. So, but for a given integration time, these can be compared. So with a low resolution spectrograph, up here, the rotation velocity is relatively high. So in this formula, here you are limited by the V sin I term. It doesn't really matter whether you build a spectrograph that has a resolution of 20,000 or 80,000 or 100,000. Down here, you are limited by the spectrograph resolution, and here it pays off. If the star is a slow rotator, it pays off to build a spectrograph with higher resolution. So we settled for something like 80,000, because if you then get higher and higher, you still gain a little in your measurement precision, but not that much, and things get more expensive and bigger and so on. So 80,000, we thought, is a pretty good compromise. It allows us to take advantage of the best precision that we can get on the slowly rotating stars. The second question that you should ask after you know the resolution of your spectrograph is, at which wavelength should my spectrograph work? So here, you have the spectral energy distribution of an M-type star. So this is roughly the spectrum of an M-type star. Here is 2 microns, 1 micron, half a micron, or 5,000 angstrom down here. And this is the range where most of the existing radial velocity spectrographs measure. Yeah, they use either an iodine cell, which works between 5,000 and 6,000 angstroms, or like HARPS, they have a wavelength range that covers the range between something in the blue to UV. HARPS measures from 3,800 to 6,700, so also down here. Clearly, this is not the range where M stars emit most of their light. If you are interested in M stars, you should build a spectrograph that works in this wavelength range, around 1 micron. So this pushes you into the near infrared. Now this is not the whole story, of course, because if you want to measure the radial velocity of a star, what you need are sharp absorption lines. If the star doesn't have any absorption lines, you cannot measure the radial velocity. So we have to look at the spectrum, and so here these are models of spectra, mostly because spectra at high quality covering this whole wavelength range essentially do not exist. But in these models, if you look at this wavelength range here, around 1 micron, a little bit longward of 1 micron, you see a large number of nice and strong lines. This is the so-called Wideband, and this is great for measuring radial velocity. If you look at around 1.2 microns, somewhere here, you see the spectrum is not nearly as rich in information. So if you want to optimize the wavelength range in which your spectrograph should work, you have to take both factors into account. How many photons do I get? That's the previous view graph that tells me where's the peak of the SED. And the second question that you have to ask is, how much information is there? How much information do those photons carry? And the more spikes I have in my spectrum, the more information there is. And so if you put all of this together, you get a plot like this. This is for an M4 star at 3 different spectrograph resolutions. Again, the whole view graph is done for one specific integration time that you use. You can get better numbers if you just integrate longer, but it's all points are done for the same integration time. And here you see that actually the red part of the visible wavelength range does fairly well, and the reason is that this is not so good from the SED point of view, but there's a lot of information in the stellar spectra here. Also, this range that I pointed out around 1 micron does very well, and the range around 1.2 microns does not do nearly as well, because here you don't have enough information. So what this suggests is building a spectrograph that perhaps works in the red part of the visible, or here out in the range just beyond 1 micron. Oh, by the way, I'm taking visible in the loose sense that it is visible to silicon, not to the human eye. So the boundary between visible and near infrared, as most astronomers think today, is it's visible if you can use a CCD detector in your spectrograph, which works out to roughly 1 micron, where you hit the band gap of silicon limit. And anything beyond 1 micron, you need infrared detectors is in the infrared wavelength range. So this suggests that perhaps we can get away with a spectrograph that works with a silicon detector. This one, if you want to use this part of the wavelength range, we need an infrared spectrograph. We decided to do both. And there's a specific reason for why we did that, and that is jitter or variability of the spectrum due to stellar activity. So this is a very extreme example where one of our colleagues, quite some time ago already, took data on, this is a very late M star, M9 star, with a visual spectrograph, and he got these black data points, and this looks like a nice planet detection. Very nice sinusoidal fit. But then he went and looked with an infrared spectrograph and got these points, and you don't see anything. So that's not good. If you have a planet, all lines should shift by the same amount no matter in which wavelength range they are, because what you are looking for is a physical motion of the star in its orbit. And so similar things to this have happened a number of times to different groups. They went and observed with a visible light spectrograph, published a planet, and somebody else came with an infrared spectrograph and said, oh, no, you fell into the trap of stellar activity. And we didn't want that to happen to us, so we said we'll build visible and near infrared, both of them, to start with, so that we can observe all the time with both spectrographs. So you can look at this in a little bit more detail and actually simulate star spots. So this is a very primitive simulation in a way. Here is a rotating star which has a spot, and the question is what happens to the radial velocity. And there are two effects that you have to take into account. One effect is the convective blue shift. At the surface of the star you have convection, and the convection pattern is different in the region of a star spot. Convection in the star spot typically is suppressed, and around the star spot it's enhanced because of the magnetic field structure. You can have spots that have an increase in the total convective blue shift, or you can have one that has a decrease. In any case, you have a signal that when the spot comes into view, it's small, and then when it gets to the center of the star, it gets largest, and then when it disappears on the backside of the star, it's gone again. So this is the signal of the convective blue shift that normally if you have a uniform stellar surface, it's going on all the time, and it just shifts the average of the line. But now, as the spot modifies this and moves across the surface of the star, you get this signal as a function of time. There's a second effect, and that is due to the rotation of the spot. So the spot is blocking some light, and when the spot comes around here, the star rotates this way, the spot comes towards you, it blocks some light in the blue shifted wing of the line. So this is a net redshift of the line. If line that is blue shifted is blocked, there's less of that. The total radial velocity that you measure is a little bit redshifted. And then it moves across the surface in the center. It blocks light at the center of the line, then it moves and blocks light that is on the red wing of the line, and the total radial velocity signal is this. And so this is the sum of the two signals. So this is going to happen if you have a star, a rotating star with a spot, and you observe that star, you get a signal that looks like that as a function of time. And if the spot is there and is very long-lived, it comes around and around and around, it looks like a periodic signal that you could confuse with the signal of a planet. It's not a sine curve or a Keplerian signal, but if your signal to noise is limited, or if you have several spots, what you can see, or what you see, you could easily mistake for the signal of a planet. Now, if you look at this a little bit more carefully, this signal is different in the blue and in the red part of the spectrum. This has all to do with temperatures. Yeah, it's up. And if there are temperature differences, they are always have a higher signature, a larger signature in the blue part. If you think about the difference of two Planck curves, the difference is biggest in the blue and smallest in the red. So the signal is slightly chromatic. It's not exactly the same at all wavelengths. And this is shown here. If you take these two curves, one is at 800 nanometers the other one at 1300. So this would be measured with our visible spectrograph. This would be measured with our infrared spectrograph. And you take the points here and just connect the point on the blue and the red line, you get a diagram like that. So here you have a larger spread. On the blue line, the amplitude is larger, and the spread is smaller in the red part. And so remember this shape, because I will come back to it. Now this is a signature that what you are seeing is a star spot and not a planet. In a planet, the blue and the red would always be exactly the same, and all these lines would be exactly horizontal. So with all of this background, here are the guiding principles for our instrument. This is what we set out to do. First of all, CARMENES is a single-purpose instrument. We built it specifically to look for planets around M dwarfs. Therefore, we need high stability. So this is thermal and mechanical stability, very stable input. We wanted no moving parts in the spectrographs that could disturb anything. We want high resolution to take advantage of the slow rotators and get the best possible measurement precision for them. The large wavelength coverage, because that allows us to discriminate against intrinsic variability, and of course high efficiency. So and this is the layout that we came up with. There's a front end that is attached to the telescope. So this has the optics in it that take the light from the telescope, and then they send it into optical fibers. There are fibers coupling to the near-infrared spectrograph and the visible spectrograph, and because the two spectrographs are supposed to be very stable, they are in vacuum tanks, and these vacuum tanks are temperature controlled. And there's calibration light that we can send in that then also goes through these fibers into the spectrographs. The principle of these spectrographs, so that's in the name, CARMENES, these are Echelle spectrographs, and these are so-called cross-dispersed Echelle spectrographs. Echelle spectrograph means you are observing in a very high order. Remember from your optics lessons, the resolution of a spectrograph is proportional to the order in which you observe. We observe very high orders. And if you do that, then the light comes in, it's reflected by this Echelle grating. The different orders overlap. Yeah, for instance, the wavelength of 5,000 angstroms in the 101st order is exactly in the same location as 5,050 angstroms in the 100th order. Because in the grating equation you have a term n times lambda. So different wavelengths in the different orders fall on the same place. And you can now either put in a filter and cut out one order only, but that is not very efficient. What we do in such a design, in a cross-dispersed, we put in a cross-disperser that is a prism or a grism that has some dispersion in the orthogonal direction, so that the red orders are in one part of the detector and the blue orders are at the other part of the detector. Yeah? So you have two dispersing elements, a high dispersion element in one direction, a low dispersion element in the other direction, so that the orders now are in a two-dimensional arrangement. So it looks like this. This is our visible. These are real data from our spectrograph. Yeah, this is a 4K by 4K CCD detector. And you see all the individual orders. So these are the lower orders. These are the higher orders. And up here we have two infrared detectors. So they are just put together in this image here. In reality, they are in a different vacuum tank, these detectors. And the total that we observe is 28 infrared orders, 61 visible orders. And the length of each orders is 4,000 pixels. So we have 89 times 4,000, or nearly 400,000 pixels in each spectrum that we take. So it's a very nice instrument if you're interested in taking a spectrum of a star with a lot of information in it. You get 400,000 pixels in one spectrum in each shot. So this is a little enlarged part. And you see this is a calibration source. We have a Fabry-Perot that has a very regular grid of lines. For calibration purposes, this is a stellar spectrum. And the stellar spectrum, of course, has lines. So the measurement that we are interested in making is we want to observe these lines in the stellar spectrum go back and forth by about 1 meter per second. So our measurement precision here corresponds to 1/1000th of a pixel. Or this is about 10 silicon atoms on your CCD. If the star shifts by 10 silicon atoms on the CCD, that's what we want to measure to discover a planet. And therefore the whole instrument has to be extremely stable, because if the detector moves, then all lines move in the same way, and you do not have your square root of 1000 advantage of averaging, because all of them move together. So the properties is the visible covers the red part of the visible wavelength range, the resolution of about 90,000. It's in a vacuum tank, temperature stabilized, with a 4,000 by 4,000 pixel detector. The near-infrared spectrographs covers also from about 1 micron to 1.7, just slightly less resolution. This one is also in a stabilized vacuum tank. It has to be cooled down to 140 Kelvin so that we are not swamped by the thermal radiation of the spectrograph. Here also we have a goal of 1 meter per second, but in the infrared it's much, much more difficult. I'll show a few images that shows you why. And here we have 2 infrared detectors. So the layout, the design of the spectrograph is fairly classical. Here's an optical bench. Here's the camera of the spectrograph in the background, slanted like this, is the shell grating. Here's the collimator. So the light path is somewhere here. The optical fiber comes in, and from here to the collimator to the grating, back through the cross disperser into the camera. Yeah, so you have to make the spectrograph very stable. You also have to illuminate it in a very stable way. And this is difficult. If you think about bolting your spectrograph to a telescope, you have a slit, and what the spectrograph does at any given wavelength, it takes an image of the slit and makes an image of the slit on the detector. And if that slit moves a little bit, the image moves a little bit on the detector. So if the illumination of the slit changes because of seeing or because of guiding errors of your telescope, the slit image on the detector will also move. And remember, we want to measure with a precision of 1/1000th of a pixel. So we would have to keep the image of the star on the slit constant to 1/1000th of the slit width. And that's impossible. No telescope in the world does this. And no adaptive optics system in the world does it at that precision. So it's very important to have these fibers in the light path, because the fiber decouples the motion of the star on the input from the output. The output of an optical fiber is much more stable than the input. But there's a problem if you take a circular fiber, and if you think about the light path in the fiber as in a ray optics approximation, the angle at which the light bounces around is always the same. So the impact parameter never changes. So if you illuminate a round fiber and have with a point source that's a little bit off center, what comes out in the end is not uniform, but it's a little ring, because the rays never change the angle that they make. And therefore, the fibers that we put in have a section that is octagonal in cross-section. So these are specially drawn fibers with an octagonal cross-section, And an octagon does not have this property that a circle has, namely that if you bounce around a ray, you get much more uniform illumination in octagon. So this is, for those theoretically inclined, you can think about this in 2 dimensions almost as a billiard, and you want to have an ergodic billiard as the cross-section of your fiber, which is much better than any other. So this was a PhD thesis, or a large part of a PhD thesis here at the Landessternwarte, to test fibers with different cross-sections that give the best decoupling from input and output. And so you see here, you can move this. This is a little single-mode fiber. This was moved across the input. It moves a lot. It moves by almost 1 diameter of the fiber, and you can't see anything at the output. So you want this very strong decoupling of input and output for stability. Yeah. So this is the near-infrared spectrograph during the integration phase. It was put together by our colleagues in Granada. We built the visible spectrograph here in Heidelberg and also the front end. Then the vacuum system for the visible spectrograph was also integrated here. It was done in collaboration with the Max Planck Institute for Astronomy. So this is in the integration hall at MPIA. This is the spectrograph now wrapped into a radiation shield inside the vacuum tank. The first component that we put on the telescope was in April 2015. This was our front end. So here's our front end, and you see that this is a completely different instrument that's attached to our back. We have a mirror in the front end that we can pull out, so we can switch very, very quickly between CARMENES and other instruments that can be attached to the back of our front end. Our light goes into fibers that you can see here. But we started in April 2015 doing tests on the telescope, and then a little later in the year, we drove our vacuum tanks down. So here's the visible on a crane being lowered into its final place, which is 1 level down from the telescope. And here comes the near-infrared spectrograph also being lifted down into the, onto the dome floor here and then down into its final location. Here it's installed at the telescope, and then we got first light. This happened in November 2015, and here's a screenshot. Here you have the spectrum of a star, and here's this calibration etalon. Here you can see some lines. These are not stellar lines. This is the oxygen A band in our own atmosphere. And so starting in late 2015, we actually started commissioning the instrument, testing it at the telescope, and then started our survey. So here's a very simplified view of what you have to do once you get a spectrum on your detector that looks like this. The first step is you have to extract your spectrum. What you get is the output of a CCD, which is 2-dimensional. You want flux as a function of wavelength, which is 1-dimensional. So you have to apply a wavelength solution. You have to know which pixel corresponds to which wavelength, gridding of the spectrum, and so on. You have to calibrate the flux and the wavelength. So the information that you get from lamps, from your Fabry-Perot, has to be applied. You have to correct for the tellurics. So that's the absorption of our own atmosphere. And then compute the radial velocities, which is normally done by cross-correlation with a template, and then you have to shift from the reference frame of the telescope to the barycenter of the solar system. So the first step, after the first step, the spectrum looks like this. This is extracted spectra, so now from, say, an image on the CCD, you go to flux as a function of pixel number, or then after calibration of wavelength. This is shown here order by order for the visible and the near IR. This is the telluric absorption that you have to correct for. And here you see that the wavelength range that we have picked is great from the point of view of the stellar astrophysics. You want to look at M stars where they give the best signal, but our atmosphere is quite nasty in this wavelength range. There are lots of bands, mostly water, but also oxygen and carbon dioxide, and you have to clean your spectra from all this mess that's on there that otherwise will corrupt your measurements. And again, there are nice wavelength ranges, or rather good wavelength ranges, and there are others that are completely lost and that you just have to forget about. And then after you've done this, you get spectra that are great for doing astrophysics. So this is a few small sections of a spectrum of a star that has been fitted with a stellar model atmosphere. So the red parts of the spectrum are those that have been fitted, and the blue parts have not been used. So where the spectrum, the underlying spectrum has not been used in this part. For instance, in the red part, it has been used to determine the effective temperature, the gravity, and so on of that star. So this is the first step that one normally does. If you get a nice high-resolution spectrum of the star, you use that to determine the effective temperature, the gravity, the metallicity, and so on. The full spectrum looks like this. It covers the range from 5,000 angstroms to 17,000 almost completely. Here we have small gaps in the near IR because our detectors are not large enough. But you see the amount of information that is there. And in this case, this is an active star. It has H alpha in emission, YZ CMI. And this is a small section of a spectrum of stars of different types. This is the sodium D doublet. You see this star here has these lines very strongly in emission, so this is an indication it's very, very active. Other stars have tiny emission lines here, and we can use that to sort our stars into bins. The good ones, the bad ones, the ones that have strong emission lines are probably very active and not so good for our radial velocity measurements. These variability indicators can be variable, time variable by themselves. So here are 3 spectra of, again, this star YZ CMI, where H alpha also varies. This is a non-active star for comparison. So this is another piece of information. You can look at the strength of these variability indicators. You can also look at their time variability and decide whether you want to observe this star a lot. And here is a plot that shows this effect that I explained before when I showed the rotating star, the model of the star spot. Here we have computed the radial velocity separately for each order of the spectrograph. And these are the blue, and these are the red orders. And you can see that the effects that I asked you to remember, namely that the lines converge in the red, is seen here. So this is a clear indication that we see radial velocity variability that is due to a star spot, not to a planet. So this is great for several reasons. One is we don't publish a paper that is bogus. And second, we can learn a lot about the star by itself. By looking at these slopes, we can learn something about the star spot temperature and the star spot distribution and so on. We are preparing a stellar library because this is the only spectrograph in the world that can cover this wavelength range at this resolution. There's no stellar library that covers our spectral wavelength range. So these are spectra from O stars to M stars that we have taken that will come out very soon, that are very useful as a reference for reference grid for stellar atmospheres, for instance. And here are some radial velocities. So we started, of course, by looking at stars that have known planets. GJ436 is a very well-known M star with a well-known planet. The amplitude here is 17.5 meters per second. The mass of the planet is 25 Earth masses. The gray points are from the literature. The red points are our points. And you can see that our spectrograph, we would have discovered this planet very, very easily if it hadn't been known before. We can compare how well we are doing with other existing instruments. This is a comparison with HARPS. So here we just plot the RMS that we see around of a star. We take many radial velocity measurements. We just take the data and compute the RMS. This is our histogram, and this is HARPS. And they're virtually identical. And that tells you that the scatter that you see is not dominated by your measurement precision. It is dominated by the radial velocity variations of the stars themselves, mostly due to activity and spots, possibly also some of that due to planets. So essentially, our time series are as good as what has been done before. And this is another experiment that we have been making. We have been looking at a few transiting planets to do transit spectroscopy. And so in this case, which is not an M star, we see the absorption in the atmosphere of the planet in the two sodium lines. So this planet has sodium, and we see the additional absorption when the planet transits its parent star. So to summarize the status, the visual spectrograph throughput and quality are okay. It's very good for doing stellar spectroscopy. We have a full data reduction pipeline that's working and giving us data. We have many stars that we see that have a scatter that is less than 2 meters per second. So we don't really know whether our spectrograph fulfills our goal of 1 meter per second, because we do not have any standard stars that are stable at that level. We know that we have a number that are better than 2. So this is an upper limit on our internal spectrograph stability, and it takes more work to figure out where we are between 2 meters per second and better. As I showed, the distribution is very similar to HARPS, so we are limited by the stellar noise, not by the spectrograph, and we have tests of transits. The near-infrared spectrograph is a little bit behind, which is not surprising, because it is much more difficult and more different than what had been done before. Again, also as a stellar spectrograph, it's a great instrument already. We are still doing what we would call something like beta testing of the data reduction pipeline. We need to do more work, for instance, on telluric absorption. We have done some recent hardware improvements also. We are already better than any other instrument. Namely, we get something that is better than 10 meters per second kind of out of the box. We see that within one night we get to about 2 meters per second. So there's something in the calibration that we have to improve to get to these 2 meters per second or better also over longer time scales. And I had prepared a few more slides on possible future plans, but in the interest of time, I think I'll stop here. Thank you very much.
So, thank you, Andreas, for this very nice overview of CARMENES, how it has developed, what one needs to take into account when designing such a complex instrument, and some of the first results. Very impressive. The podium is open for questions and discussions. I start here.
Thank you. So what was the size for the planet with the atmosphere, and what kind of a star was the host star?
this is one of the easiest transiting planets. So this is more or less a solar-type star with a relatively large planet. So we are starting to work on data reduction methods, wanted to see how this works. So in this case, one of the interesting things is looking whether in addition to sodium, you would also see potassium, for instance, which cannot be done by HARPS because it's outside the HARPS wavelength range. We're also looking for water in the near infrared, which is much more difficult because it's in a part of the atmospheric, there's a lot of telluric absorption very nearby, so much more difficult. But it looks very encouraging that we...
Do you expect to see some sort of signature from super-Earths or kind of mini Neptunes?
Yeah, of course, super-Earths, mini Neptunes will be pushing it. We don't know yet what our limits are, neither from the stability point of view, nor, the other one we can calculate, of course, we are at a 3.5 meter telescope, not at an 8 meter telescope. So from the photon point of view, of course, it will be hard to compete with 8 meters.
Richard?
Hi, I wanted to know if you have to take into account resonance modes of motion of the atmosphere of the star, seismology, or whether you can detect it.
Okay. I think we would not have problems in detecting it. So this was done quite intensely a few years ago. When HARPS was new, there were several campaigns to do astroseismology of G-type stars. It was quite successful, but in a way, this whole field has changed a lot with Kepler. A spectrograph like this is very good to detect stellar oscillations, but it takes a lot of resources. These HARPS campaigns were 1 week or even longer to get the oscillations of one single star. Whereas now from Kepler, we have hundreds of stars. So the motivation has gone a little bit away to do this with high-resolution spectroscopy because photometry from space is so much more efficient. There are still some people that are interested in looking, in using CARMENES to look for oscillations of M dwarfs, but it will be very tough because, as we know, as you go down on the main sequence, the oscillation amplitudes get a lot smaller. So there's interest in it, but it's in a tough region compared to space photometry.
So Matthias?
Yeah, about a third through your talk, you had a collection of spectra going down to M9, where you could see a break in the spectrum near 1250 nanometers. Where's that? What is that due to?
Here?
No, much earlier.
Here?
No, forward, massively forward. Fast forward. Coming. Yes, here you can see it very clearly. So in this M9 star, there's a very sharp break at 1250.
Yes.
Sorry, 1350.
Yeah, I think this is water.
Is that telluric or stellar?
I think these are models without telluric absorption.
Ah, so it's intrinsic to the star.
This is intrinsic to the star.
But you can't use it because of the telluric bands.
So it would be very difficult, and this is why this is shaded in gray. So what we did in this simulation is we took the stellar spectra without telluric absorption, and then we said separately some bands we can observe in, and these are the black bands. So this is the Y. These are the Y band, Z band, J band, H band, and so on. And the gray bands, we will probably never be able to really get good data in because of the Earth's atmosphere.
Okay, thanks.
So they were not taken into account in this. So here we took just the wavelength ranges that are relatively clean from Teluric's point of view.
Andreas, you mentioned when commissioning started and first light was. Now, in what status is the project now, and how many nights do you expect? How many calendar years would this correspond to?
Yeah, so we got a total of 750 nights to do our survey, and we started on January 1st, 2016. So we are now running. We have had about 150 nights so far, and we will get a large fraction of that before the end of next year, and then we will have to talk with the observatory how we get the remaining nights. But we will have something of order 400, 450 nights covered by the end of 2018. And so we have now observed essentially all of our 300 stars at least a few times, and we have interesting candidates, and we are working on improving our pipeline and data reduction. There are still some glitches and bugs in that, and B, in identifying the most interesting objects. We see some RV variations. Now we have to sort out, are these due to spots or are they due to planets? And another thing is that it seems that if you see one planet, normally there's another one. And that makes it a lot more complicated. So these nice RV curves where you see one sine curve are the exception. And in many cases, you see several peaks in a periodogram, and you have to figure out, is this one planet, is this two planets, is this perhaps a mix even of eccentric planets also give you separate peaks and so on. So we are in that phase now, where we are starting to classify stars into interesting and boring and analyzing what exactly there is.
The second question, you emphasize that one can easily be misled by sinusoidal fluctuations in the visible and flat curves in the infrared due to stellar activity. Now, how many published RV planets have been withdrawn in the 22 years since this has been employed? Fake planets?
I don't know the exact number of planets that have been withdrawn. It's not extremely large. I would guess that it's maybe a couple dozen. So compared to the many hundreds that have been published, it's not very large. But a few of them were quite prominent because there were there are disputes about planets around young stars, for instance. So whenever the activity is larger, then this trap becomes bigger. And so the M stars are more active than solar-type stars, so we have to be more careful. And of course, we know that some other stellar types, young stars, giant stars, and so on, are also more active than sun-like stars. So amongst the sun-like stars, this rate is really quite low. I believe that there are more false positives that have been published in those classes of more active stars.
Andreas, I was wondering about the wavelength calibration, since you showed that now in CARMENES Fabry-Perot is used. As far as I know the story, you even bought within the CARMENES project many thorium-argon lamps. Has that now been decided to use these Fabry-Perots throughout?
Okay, so I cut that part a little bit short. Of course, I could go on for many hours about technical details. Calibration is a very interesting one, and we haven't solved all the problems yet. Many other spectrographs are calibrated by emission line lamps, and so I showed those spectrograms where, here you can see it. For instance, we had foreseen to have, in the second fiber, to have an emission line lamp, a thorium-argon lamp, or in the case of the infrared spectrograph, a uranium-neon lamp. And this is, for instance, the strategy along which HARPS was developed, and we thought we would do it the same way. Now there are two problems. One is that these lamps are of quite uneven quality, and apparently our lamps are not quite as good as the lamps that HARPS has, and this has to do with regulations about manufacturing these lamps. As the names say, they contain either uranium or thorium, and handling these materials is highly controlled, and there are laws. So today, most of these lamps come from sources somewhere in the third world, and the distribution companies don't really want to know where exactly they were manufactured and how exactly they were done. So quality control is not very good, and that means the quality fluctuates. There's a second problem that is even more severe, perhaps, and that is that you need a buffer gas, which is either argon or neon, and these elements have very, very bright lines in the red part of the spectrum. And HARPS doesn't observe there. HARPS goes up to 6,800 angstroms, so it doesn't see all the bright lines at 8,000, 9,000, but they are smack in the middle of our wavelength range. And so if we put a lamp spectrum in the lamp light in the other fiber and expose or make it bright enough to have a sufficient number of thorium or uranium lines for our calibration, then there are some very, very, very bright lines of neon or argon that bleed across the detector and that creates stray light and all kinds of problems. Very horrible. And so we decided that we can't use that, and we'll use a Fabry-Perot etalon instead. Fabry-Perot etalons are very, very nice in the sense that they give these very regular lines across the whole wavelength range, very regular everywhere. The problem is, of course, that a etalon by itself doesn't give you an absolute wavelength standard. If the two plates of the etalon shift a little bit with respect to each other, you shift the whole etalon spectrum. And although our etalon is temperature stabilized, it is not directly tied to some atomic standard like an emission line lamp is. It's always the same element. So what we do instead is we use our lamps and the etalon during daytime, in the morning and in the afternoon, and cross-calibrate our etalon against the lamps. And then over the course of a night, our etalon is stable enough to provide the reference during the night. And so we go in these two steps for the calibration.
Okay, second to last question.
Okay, fine. It's just a trivial point, but I was wondering, since you mentioned that you want to see line shifts by a dozen silicon atoms used in Egypt, I was wondering if seismic noise is in fact a problem.
No, seismic noise is not a problem. First of all, and even at sites like La Silla that have a lot more going on than Cala Alto, there's no very strong background. So during an earthquake, you would have a problem. But there are earthquakes, and yes, you may have to redo your calibration after the earthquake. But the level is not high enough. So it's not like a gravitational wave detector or something like that, where you would be limited really by the ever-present background noise. Of course, yeah. Of course. Yeah. That would be nice. No, we are not that good. Of course, our spectrograph is decoupled, for instance, from the dome. Yeah, there is a pillar and concrete, and the dome itself rests on a different piece of concrete, so that when you rotate the dome, for instance, the vibration from the dome is not transmitted to the spectrograph. Yes, at that level, of course, we would be sensitive to vibrations, but some reasonable vibration isolation and you're okay.
So let me take the liberty to ask the last question. What about atmospheric fluctuations, turbulence, and so on and so forth? Do you need to correct it, or is this just at a wavelength or at a velocity that you don't really worry?
Yeah, so the atmosphere, of course, does many different things. One is, or what I mentioned, is the telluric absorption. And of course, that is quite variable. And so that is a bit of a headache. And we are still experimenting with the best algorithms. And we will probably be still experimenting for quite some time in optimizing these algorithms to subtract the telluric absorption. The turbulence by itself, the biggest effect that it does is that it creates seeing, which moves the star around on the slit, and that's why we have the fiber in there, and that's why we have an octagonal fiber to decouple the spectrograph from that. But that is not by itself introducing a wavelength shift. The telluric lines, of course, they do shift due to wind, for instance. So if you want to use them as a calibration, then you have to worry about it.
Good. Before we thank Andreas, let me introduce next week's speaker. Selma de Mink from Amsterdam will also speak about stars, but now 2 stars in a stellar marriage, on the rare stellar marriages that live happily ever after to eventually merge as binary black holes. So she's looking into the effect and efficiency and long-term evolution of binary evolution, eventually leading to black holes and, I guess, making predictions for gravitational wave detection and so on and so forth. And with that, let us thank Andreas again.